If we have a collection of users and we want to retrieve some information about a particular user, maybe it's their age or their email address, we're going to need to search through the collection in order to find the uh, right value in the collection. There are two main ways that we can do this. We can do it with linear search and we can do it with binary search. We start off with a collection. Again, we're using an array. We can use a linked list, but in this case, the collection isn't growing or shrinking, so we're using an array. We also have this new target field down here. Now, we can't search a collection of values if we don't have any values in the collection, so let's fill these out. Maybe we said a list of users or a collection of users before, so let's go with Alice, Bob, Chris, Dave, and Emma, and Frank. If we want to retrieve information about the user Frank, so we would type Frank into the target here, we can do that really quite intuitively using linear search. Linear search, I haven't made a visualization for it because it's so intuitive. All we do is we look at the first item, Anna and Frank. Those aren't equal to each other, so we move on to the next value in the collection. We've got Bob and Frank. They're not equal, so we move across again and again and again. And when we finally find a match, that's when we stop. Now, linear search is really easy to implement. We just search through every single item in the collection and we do a comparison against the target value that we're trying to find. The downside is it can be very, very slow. You see, we've had to check every single value in the collection. This isn't always the case. If we were searching for Alice, we would only need to do one check. But on average, we're going to have quite a lot of checks that we need to do. In the last video about bubble sort, I mentioned that binary search requires the collection to be sorted in order for binary search to work. And what does that mean? What can we do with the collection if it's in order? Well, if we just check the middle item, in this case, we've got a collection of length 6, so we have two middle values. We've got Chris and Dave. Usually in binary search, we just go to the left if we have two middle values, but it doesn't really matter too much. We've gone to the middle value. We've got Chris here. And if we're comparing Chris to Frank, if and only if the whole collection is sorted, we can make an additional assertion. We can say that Frank is not equal to Chris, like we could with linear search, but we can also say that Frank, our target value, should come alphabetically after Chris, or maybe if this was sorted in reverse order, and we'd have Frank this side and Alice this side, we would know that Frank needs to be the left of Chris. In this case, we know that Frank should be on the right of Chris. This is quite powerful because we've only done one check so far. We've gone to the middle and we found Chris and we've done one check. And what we can say is that Alice and Bob are not going to be equal to Frank. We can rule them out without even doing a proper check because they are left of Chris. Every value left of Chris is going to be alphabetically before Chris. Our target is alphabetically after, so we can just completely ignore these. We know that Chris is not a match either, so we can rule out Chris, and we effectively have a new collection of size 3, Dave, Emma, and Frank. So if we do another check on these three, the middle value now is going to be Emma, so we go to Emma. Emma is not a match. We know that Frank should be right of Emma. We don't even have to check Dave. We go on to the collection of length 1, or depending on how you look at it, you can just say, okay, it's the last value, it must be this one. and we check the value and it is indeed equal to Frank. And we've got here that we've found the target value. Binary search allows us to find values in a collection on average much quicker than linear search. With binary search, we've done 3 checks. We checked against Chris, we checked against Emma, and then we checked against Frank, which was our final match. Whereas with linear search, we had to do all of the checks from Alice through to Frank, which is 6. There are some cases in which linear search will find your value quicker than binary search. For example, Alice with linear search would be the first item to be checked, whereas with binary search, we first check Chris again, and then we need to check this list, the collection of 2 values, and so we're going to check the one on the left, and so we've required 2 checks in order to find Alice instead of linear search that has 1. So the first few values, the leftmost values, may be quicker to find with linear search than binary search. In fact, the actual first item is almost always quicker with linear search than binary search. The only exception to that is if the collection only has 1 value in it. Or 2, actually, thinking about it. But overall, we can say that binary search is faster. And if you're still not convinced, let's say instead of a collection of 6, we double it. Let's say we have a collection of 12 items. The average amount of checks that linear search will have to do to check a collection twice as big is also going to double the average. Linear search, on average, with a collection of 6 items, is going to have to do about 3 checks. 3 checks will get to half of the collection, and so that's kind of the average. If we double that, if we have 12 values to check, the average is going to go from 3 to 6. We double the size of the collection, we double the amount of checks that a linear search has to do. Whereas with a binary search, we are ruling out half at once. So if the collection was to double in size from 6 to 12, we do 1 check and we are left with a collection of size either 5 or 6. And that's back where we started. So a collection of length 6 in a binary search only has to do, a collection of length 12, which is double the size, only has to do 1 more check than a collection of length 6. So overall, as your collection gets bigger, binary search becomes more and more efficient. The only real downside to binary search is that it must be sorted. The collection must be sorted in order for binary search to work. And let's just have a look at why that's the case. Let's swap Alice and Frank round. So now the collection is no longer sorted in order. Let's target Frank again, and you'll see that when we do the first check, I've implemented a sort button there, so we'll need to check it manually. If we check the first item in a binary search, that's going to be Chris. And what we're going to say is Chris is not equal to the target Frank, and so we're going to need to do another check. But Frank, our target, should be right of Chris, so we can rule out the whole left side of Chris. But that's actually where our value of Frank happens to be. Because we are kind of assuming that Frank is going to be on the right of Chris, That means that we have to have our collection sorted in order. There are cases where a binary search can still work with the collection not being in order, but A, it might just not work. We might not find the value at all. And B, it might not even be as fast because everything becomes a bit distorted when we're doing it like that. So that's been linear search and binary search. In the next video, we'll look at Prim's algorithm.